A single Mars mission would expose an astronaut to more than twice NASA's entire career radiation limit. And that's before they've even unpacked. If you find that number unsettling, stick around, because by the end of this video, you'll understand why the radiation is actually one of the more manageable problems, and why the real barrier to returning from Mars is written not in orbital mechanics or fuel chemistry, but in the quiet cellular language of your own body. If this kind of deep science storytelling is what you're here for, hit like and subscribe now. It genuinely helps keep videos like this coming. Mars is the obvious next step. It's rocky, it has a thin atmosphere, it has water ice, it has a day that lasts almost exactly 24 hours, and it sits close enough that our telescopes can see dust storms rolling across its plains. The Apollo went to the moon and came back 6 times. So why is Mars fundamentally different? Because the moon is 3 days away. Mars at its closest is roughly 55 million kilometers away. And that's a rare alignment that only occurs once every 26 months. The average distance, factoring in where both planets actually are in their orbits across a typical mission timeline, is closer to 225 million kilometers. The moon is a camping trip. Mars is emigration. And the distinction matters more than almost anyone discussing this mission in public has been willing to say clearly. Let's start with the orbital constraint, because it shapes everything else. Earth and Mars don't orbit the Sun at the same speed. Earth completes a lap every 365 days. Mars takes 687. This means the two planets only line up in a favorable position, what astronomers call opposition, roughly every 26 months. Miss your launch window and you don't wait a few weeks, you wait 2 years. There is no shortcut. You cannot decide halfway through a mission that you'd like to come home early. The orbital mechanics do not care about emergencies, equipment failures, or the fact that someone's bones have deteriorated faster than the models predicted. The window either exists or it doesn't, and when it doesn't, you wait on Mars. This constraint creates the minimum mission profile that drives all the biology. Approximately 6 to 9 months traveling to Mars, then a surface stay of roughly 18 months waiting for Earth and Mars to realign, and then another 6 to 9 months returning. Add it up. The very shortest realistic mission is around 2.5 to 3 years. 3 years during which, every single day, the human body is being reshaped by an environment it was never designed to survive. Not reshaped temporarily, reshaped permanently. To understand why that matters, you have to appreciate something about how the human body works. It doesn't maintain your skeleton, your muscles, or your cardiovascular system out of sentimentality. It maintains them because they are being used, and it scales exactly what it builds to the demand it detects. Gravity, the invisible force pressing down on you every second of your life on Earth, is the fundamental driver of that demand. Your bones are dense because gravity requires them to be. Your heart is strong because it pumps blood upward against gravity roughly 100,000 times a day. Your leg muscles are powerful because they carry your full Earth weight through every step. Remove gravity, and the body doesn't maintain those systems. It dismantles them, ruthlessly, efficiently, and in some cases permanently. The numbers make this concrete. In microgravity, the weightlessness of deep space transit, astronauts lose approximately 1 to 3% of their bone density every single month. That doesn't sound catastrophic until you extrapolate it. After 6 months, that's potentially 18% gone. After a year, up to 36%. A Mars mission's transit phases alone, roughly 12 to 18 months of total weightlessness across the round trip, could account for bone loss in that range, and the surface phase on Mars adds more, because Martian gravity is only 38% of Earth's. Your skeleton, which is tuned to bear your full weight on Earth, detects that the load has dropped by 62% and continues shedding what it registers as excess. The decline slows compared to zero gravity, but it does not stop. Consider the benchmark. A 70-year-old woman with severe osteoporosis has typically lost somewhere between 30 and 40% of her peak bone density. That deterioration unfolded over decades. A healthy astronaut in their 30s can approach those numbers within 2 years of a Mars mission. The bones most at risk are exactly the ones you'd need most upon returning. The hips, the spine, the femurs, the weight-bearing structures that hold you upright. The mechanism compounds the damage in ways that aren't just structural. As bone is resorbed faster than it's formed, decalcium floods into the bloodstream and has to go somewhere. It goes to the kidneys. Kidney stone risk climbs dramatically in microgravity, and kidney stones in an environment where the nearest surgeon is 8 months away represent a medical emergency with very limited options. Meanwhile, the bones themselves are not just getting thinner, they're changing in architecture. Trabecular bone, the latticed internal structure that gives bone both lightness and strength, degrades in ways that don't fully reverse even when density partially recovers. You don't just lose mass, you lose the internal geometry that made the mass useful. Muscles follow the same logic. Without gravity to fight against, the muscles responsible for keeping you upright, the leg muscles, the back extensors, are the core stabilizers, begin atrophying at rates of 1 to 3% per month. More insidiously, the muscle fibers themselves change type. Slow twitch, endurance-oriented type 1 fibers, the kind that carry you through a full day of walking, give way to fast twitch type 2 fibers that produce force quickly but exhaust rapidly. You don't just get weaker, you get a different kind of weaker, the kind that struggles most with exactly the sustained, low-grade effort that everyday life on Earth requires. Astronauts returning from the International Space Station after 6-month missions, the ISS is only 400 kilometers above Earth, well within Earth's magnetosphere, with ground support available every second, are frequently carried out of their capsules. They often cannot walk unassisted. Recovery takes weeks to months. And critically, some never fully recover their original bone density. Not ever. Now extend that 6-month ISS timeline by a factor of 4 or 5. Remove the ground support, remove the rescue option. Remove the psychological comfort of knowing Earth is just below you. That is a Mars mission. And the body doesn't know you're planning to come back. It just keeps recalibrating, month after month, for the world it's actually in. The heart deserves its own attention here, because the cardiac story is particularly bleak. On Earth, your heart is doing something remarkable and strenuous every moment of your life. It's pumping blood upward against gravity to supply your brain and upper body. That constant effort, repeated roughly 100,000 times per day, every day of your life, is what keeps the heart a powerful, thick-walled muscle. In microgravity, that vertical resistance disappears. The heart doesn't have to push uphill anymore, so it adapts. Studies of astronauts on extended missions show that heart mass can decline by up to 20%. The heart literally shrinks. At the same time, the fluid dynamics of the entire circulatory system shift. Without gravity pooling blood in the lower body, fluid redistributes upward into the chest and head. The body interprets this redistribution as excess fluid and triggers hormonal responses to shed it. Blood volume drops by up to 20%. The heart adjusts to pumping a smaller volume against lower resistance, and in doing so, becomes a smaller, less powerful pump tuned for a lighter world. The cardiovascular problem doesn't reveal itself in space. It reveals itself the moment gravity returns. That shrunken heart, adapted over years to minimal resistance, suddenly has to push blood against full Earth gravity, 3 times the gravitational load of Mars and dramatically more than the zero gravity of transit. The result is orthostatic intolerance. Blood pressure crashes when the astronaut tries to stand, dizziness follows, and in severe cases they lose consciousness within seconds of trying to be upright. After 6 months on the ISS, some astronauts cannot stand without assistance. After 2 to 3 years on a Mars mission, with radiation-induced atherosclerosis, hardened calcified arteries layered on top of the cardiac deconditioning, the cardiovascular system may simply be incapable of sustaining consciousness in one full gravity, not temporarily incapable, structurally, fundamentally incapable. And then there's the radiation. Baji, this is the one that people discuss most and understand least, because radiation does its damage invisibly at the cellular and molecular level in ways that compound silently over time and cannot be undone. On Earth, you absorb roughly 3 millisieverts of radiation per year. That's the natural background, cosmic rays filtered by the atmosphere, radon in the soil, medical imaging, all of it combined. On the International Space Station, still protected by Earth's magnetosphere, that annual dose jumps to about 150 millisieverts. Step beyond the magnetosphere into deep space and the protection vanishes entirely. Galactic cosmic rays, high-energy particles accelerated by supernovae across the galaxy, traveling at significant fractions of the speed of light, pass through spacecraft walls as though they don't exist. You can't feel them. Now, you can't see them, and you absolutely cannot stop them with any shielding technology that could be practically carried on a spacecraft. The total estimated radiation exposure across a Mars mission round trip, transit plus surface time, ranges from roughly 870 to over 1,200 millisieverts. NASA's current career radiation limit for astronauts is 600 millisieverts. A single Mars mission would exceed that limit before the crew even set foot on the planet. The damage is cumulative and irreversible. Unlike ultraviolet damage to skin that the body can largely repair, ionizing radiation shreds DNA strands directly. The body's repair mechanisms work, but they work imperfectly under bombardment and errors accumulate. Over months and years, mutations stack on mutations. The cancer risk rises. Estimates from mission modeling suggest an additional 5 to 10% lifetime cancer risk from a single Mars mission. But cancer isn't even the most operationally immediate concern. Recent animal studies using simulated galactic cosmic ray exposure show that the brain is profoundly vulnerable. Chronic inflammation develops in neural tissue. Dendritic spines, the tiny branching structures through which neurons communicate with each other, are lost. Fewer connections between neurons means slower cognition, weaker memory, impaired spatial reasoning, and reduced ability to make rapid decisions. The behavioral markers in these animal models are striking. Increased anxiety, difficulty distinguishing familiar environments from novel ones, impaired learning. These are exactly the cognitive capacities most critical when a single navigation error, a single misread instrument, a single poor decision could kill the entire crew. The human data from deep space radiation exposure is limited because no human has ever spent years beyond Earth's magnetosphere. But the animal models give no reason for optimism and considerable reason for concern. Thicker shielding seems like the obvious answer and turns out to be counterproductive in an important way. When high-energy galactic cosmic rays strike dense shielding materials, they generate secondary particles, a shower of lower energy radiation that can actually deliver a higher effective dose than the primary particles would have on their own. There is no straightforward engineering solution. Magnetic shielding sufficient to deflect galactic cosmic rays would require superconducting magnets generating fields orders of magnitude stronger than anything we've built on the scale of a spacecraft. Pharmaceutical interventions to protect against radiation damage are being researched, but nothing has been validated for a years-long deep space exposure scenario. Now add vision to the list. In microgravity, cerebrospinal fluid pressure in the skull rises because the fluid that normally drains downward by gravity no longer does. That elevated intracranial pressure pushes on the back of the eyeball, physically flattening it. The optic nerve swells, the retina distorts. Roughly half of astronauts who have spent 6 months on the ISS return with measurable changes to their vision, and some of those changes do not reverse. After 2 to 3 years in the combined microgravity and partial gravity environment of a Mars mission, The concern graduates from blurry vision, requiring new glasses, to potential permanent optic nerve damage. Not the kind of damage correctable lenses can fix, structural damage to the nerve that transmits sight from the eye to the brain. So let's hold all of this together for a moment. Degraded bones approaching osteoporotic fragility, muscles reconfigured for a 1/3 gravity world, a shrunken heart adapted to minimal circulatory resistance, radiation accumulation well past career safety limits, and potential permanent cognitive and visual impairment, all before the return trip even begins. And the return trip means 6 to 9 more months in zero gravity on top of everything that came before, if followed by the brutal reintroduction of full Earth gravity to a body that has spent 3 years systematically forgetting how to live in it. When that return capsule touches down, the astronaut stepping out, if they can step, is experiencing one full gravity for the first time in nearly 3 years. Bones that may have lost 40 to 50% of their density face the immediate mechanical stress of supporting their owner's full Earth weight. The risk of fracture from the simple act of standing is not a theoretical concern. It is a realistic expectation based on extrapolating what we already observe after 6-month ISS missions. The heart, shrunken and deconditioned, suddenly has to push blood against 3 times the gravitational load it has adapted to. Consciousness may not be sustainable. The muscles, retrained for Mars, buckle under a load they haven't supported in years. Artificial gravity through spacecraft rotation is the engineering solution most often proposed, and the physics are sound. A large enough rotating structure creates centripetal acceleration that mimics gravity. The problem is scale. To produce 1 full G of artificial gravity without the rotation rate being so fast that passengers experience severe vestibular disorientation, the kind that causes immediate nausea and disorientation, the rotating structure needs a radius of at least 50 meters. Building, launching, and operating a rotating habitat of that scale is far beyond any current or near-term spacecraft design. SpaceX's Starship, the most ambitious Mars transport vehicle currently in development, does not include a rotating section. No current Mars mission architecture does. Centrifuges for individual exercise or partial gravity exposure have been studied, but a small centrifuge providing intermittent exposure is not a substitute for continuous gravity. The fuel and return propellant problem sits alongside the biology as a structural barrier, and it illustrates why the engineering challenge amplifies rather than substitutes for the biological one. To bring enough propellant from Earth to fuel a return journey from Mars would require launching an enormous mass. Estimates consistently place it in the range of dozens to over 100 metric tons of propellant just for the ascent from Mars and the trans-Earth injection burn. Every kilogram of propellant that has to travel from Earth to Mars must itself be propelled there, which requires more propellant, which creates the compounding tyranny of the rocket equation. The mass ratios become impractical at a fundamental level. The proposed solution is in situ resource utilization, or ISRU, making propellant on Mars using local resources. The core chemistry is well understood. The Sabatier reaction can combine carbon dioxide from the Martian atmosphere with hydrogen to produce methane and water, and electrolysis can split water into hydrogen and oxygen. SpaceX's Starship architecture depends on producing liquid methane and liquid oxygen on Mars to fuel the return trip. NASA's MOXIE experiment, which flew on the Perseverance rover, demonstrated oxygen production from Martian CO2 at a proof-of-concept scale. MOXIE worked. It produced oxygen. That demonstration is genuinely significant. Yes, but there is an enormous distance between a proof-of-concept demonstration and an autonomous industrial propellant production system operating reliably on Mars for 18 months with no possibility of human servicing from Earth. MOXIE operated at roughly 10 grams of oxygen per hour under controlled conditions. Producing enough liquid oxygen for a crewed Starship return requires scaling that output by a factor of thousands. then liquefying and storing the product without boil-off losses in cryogenic tanks exposed to Martian temperature swings. You also need water, a lot of it, to provide the hydrogen for methane synthesis. Mars has water ice, but accessible water ice deposits near the equatorial regions where missions would likely land are not well characterized. Drilling or mining operations would need to function autonomously, and the machinery would need to survive Martian dust storms, which can last for months and reduce solar power availability to near zero. Every component of this system represents a single point failure. Any one of dozens of subsystems failing means no return propellant. No return propellant means no return. The psychological dimension of all of this rarely gets the analytical attention it deserves, but it is inseparable from the physical story. Communication delays between Earth and Mars range from roughly 3 to 22 minutes each way, depending on orbital position, meaning a round-trip message exchange takes between 6 minutes and 44 minutes at best, and that assumes nothing is lost in transmission. In a medical emergency, in a systems crisis, in any situation where human judgment is needed in real time, there is no one to call. The crew of a Mars mission is more isolated from mission support than any humans in history. They are more isolated, in fact, than the Antarctic winter-over crews, whose psychology has been studied as the closest terrestrial analog. Those Antarctic studies identified something researchers called the third quarter phenomenon, a well-documented dip in morale, cohesion, and psychological performance that tends to emerge when a confined, isolated group passes the halfway point of their mission and the end feels simultaneously nearer and still impossibly distant. On a Mars mission, that psychological valley would hit during the surface phase when crew members have been away from Earth for over a year, when their bodies are already significantly degraded, when they know that the return window is still months away, and when the communication lag makes anything resembling a real relationship with people back home effectively impossible. Marriages, family relationships, friendships, all maintained through asynchronous text and video with 20-minute delays in each direction. The Mars 500 simulation, which confined 6 volunteers for 520 days in a Moscow facility to simulate a Mars mission profile, found that the crew experienced significant sedentary behavior, disrupted sleep, psychological withdrawal, and motivation decline in the later phases, and that was with the knowledge that Earth was just outside the door. Permanent exile is not metaphor, it is a clinical description of what happens when a human body adapts sufficiently to a different gravitational environment that return to the original one becomes medically dangerous. The point of no return on a Mars mission isn't a dramatic moment. It isn't a single decision or a single systems failure. It is the gradual accumulation of irreversible biological change across months and years, converging with the hard constraint of orbital mechanics and the unproven gamble of ISRU, until the intersection of those three forces makes return not just difficult, but genuinely inadvisable and potentially lethal. Consider what that actually means for the near-term future of Mars exploration. NASA has Mars as a stated long-term goal. SpaceX, under Elon Musk, has articulated a vision of Mars colonization as a civilizational imperative, an insurance policy for the species against existential catastrophe on Earth. These are not frivolous ambitions. The scientific and philosophical case for human presence on Mars is real. But the near-term missions being seriously discussed, those in the 2030s or 2040s, will be sending people to Mars without centrifuge gravity systems adequate to prevent skeletal and cardiovascular deconditioning, without radiation shielding capable of staying within safe career limits, and with return propellant systems that have never been demonstrated at operational scale. The honest characterization of such missions is not crude Mars exploration with a planned return. The honest characterization is colonization, or more precisely, permanent emigration under the guise of a mission. This raises ethical questions that the space community has been strikingly reluctant to confront directly. Informed consent in this context requires that recruits genuinely understand, not just intellectually acknowledge, but viscerally understand that they are likely committing to spend the rest of their lives on Mars, that the body they take to Mars will become a Martian body, and that body will probably never be capable of functioning safely on Earth again. It requires them to understand that their children, if they have them on Mars, will be born into a gravity field 2.5 times weaker than the one that shaped every human who has ever lived. What rights do those children have? They made no choice. They did not consent to being citizens of a world that their bodies may be optimized for, but that they may never be able to leave. The ethical architecture for this does not yet exist. The human trade-off at the center of all of this is not easily resolved by calling the volunteers brave or calling the mission foolish. Both characterizations miss the substance. The astronauts and pioneers who would go to Mars would be doing something genuinely extraordinary, accepting the permanent loss of the world they came from in exchange for the chance to extend the horizon of human presence. Their bones will become Martian bones, dense enough for Mars, fragile by Earth standards. Their hearts will become Martian hearts, tuned to push blood through a body that weighs less than 30 kilograms. Their brains, carrying radiation damage accumulated across years of deep space exposure, will navigate an alien world with the cognitive tools that remain. They will be something new, not Earthlings living on Mars, Earthlings who have become Martians in the only sense that matters, the biological one. That transformation isn't a failure of engineering or a failure of medicine. It is what happens when a species that evolved over 4 billion years for a specific planet tries to live on a different one. We can build the rockets, we can design the habitats, we can write the mission protocols, but we cannot rewrite the evolutionary logic that shaped every system in the human body over geological timescales. Gravity, radiation shielding, atmospheric chemistry. Earth provided all of it for free, invisibly, for every human who has ever lived. Mars provides almost none of it, and the body, ruthlessly optimizing itself for whatever environment it actually inhabits, does exactly what evolution designed it to do. It changes. The first humans on Mars will be pioneers in the truest and most complete sense of the word, not people on assignment with a home to return to, settlers, people who understood or should have understood that the price of setting foot on another planet was letting go of the one that made them. Their sacrifice, quiet, cellular, written in the slow dissolution of bone and the gradual reshaping of a heart, will be the most profound and least visible act of exploration in human history. So here is the question worth sitting with. If you were offered a guaranteed spot on that first crew, technology, training, community, the most remarkable view any human has ever had, with the clear condition that you will never set foot on Earth again, that your body will change in ways that make return impossible, that everything you've ever known will exist for you only in archived video and 20-minute delayed messages, would you go? Tell me your honest answer in the comments, and if this kind of rigorous deep dive into the science and future of human space exploration is what you come here for, please like the video and subscribe. It helps more than you might think, and there's a lot more of this kind of storytelling coming.